This is Project 4 of Design and Manufacturing, titled Enhancing Design and Manufacturing. This is Team 16 under Dr. Hassan Rashidi for his fall 2024 semester. This group project focuses on exploring key topics presented in class, highlighting advances, innovations, and trends in engineering, particularly in design and manufacturing. Throughout this semester, the team has conducted ongoing research and documentation on notable topics, culminating in the selection of 10 favorite topics to present at the end of this course. Customer value in lean manufacturing focuses on maximizing value for customers by eliminating waste in production processes. Lean manufacturing identifies 7 key types of waste: overproduction, waiting, transportation, processing, inventory, motion, and defects, and aims to remove them. The concept of customer value drives lean practices, ensuring that every activity and resource contributes directly to what the customer sees as valuable. Applications include automotive manufacturing, where Toyota applied lean, as well as healthcare, where lean principles streamline patient care delivery. By improving efficiency and focusing on customer needs, companies can enhance product quality while reducing cost. We find lean manufacturing crucial because it aligns with operations with customer priorities, fostering customer satisfaction while driving internal efficiency. The systematic approach to identifying and limiting waste makes it possible to produce high-quality products at low cost. Incorporating lean principles into our design and production processes would enable us to streamline operations and focus resources where they create the most value. For instance, in designing a new measuring tool, we could minimize unnecessary features, optimize use, and reduce production steps, ensuring that the final product is cost-effective, functional, and aligns with customer needs. All factors that are extremely important when designing and looking into manufacturing processes. Lean manufacturing's capabilities include reducing waste, improving efficiency, and enhancing customer satisfaction. However, implementing lean requires a cultural shift and commitment to continuous improvement, which can be challenging. Additionally, it may not address the complexities of highly customized or unpredictable production environments, where flexibility may take a precedent over efficiency. Value stream mapping is a visual tool used to analyze and optimize the flow of material and information required to bring a product or service to customers. VSM provides a detailed map of each step of the production process, identifying inefficiencies, bottlenecks, and opportunities for improvement. Commonly used in manufacturing, logistics, and service industries, VSM helps organizations streamline workflow and reduce lead time and improve overall productivity. We appreciate VSM because it translates complex processes into simple visual representations, making it easier to identify and resolve inefficiencies. A systematic approach promotes collaboration across teams and ensures that everyone understands the current state of operations and what needs to be improved. VSM's ability to uncover hidden waste aligns with our goal to design efficient, user-focused systems. Using VSM in design and manufacturing, we can visualize every step of the process, from raw material to customer delivery, ensuring that no resources are ever wasted. For instance, when manufacturing a precision measuring tool, VSM would help us identify delays in material handling or assembly and implement improvements to reduce lead times and costs without compromising quality. VSM primarily strength lies in its ability to provide a clear, visual understanding of workflows, helping organizations pinpoint and address inefficiencies. However, it is a static tool, capturing a snapshot of the process at a particular moment. It may not fully account for dynamic real-time changes in operation, making it less effective for industries with highly variable production environments. The Kano model is a framework used to prioritize customer requirements by characterizing features for 5 groups: basic needs, performance needs, excitement needs, indifferent needs, and reverse needs. The model helps teams focus on features that significantly enhance customer satisfaction while minimizing effort on aspects that provide little value. For example, basic needs in a smartphone include battery life and connectivity, while excitement needs might include innovation features like facial recognition. The Kano model is widely used for production design, marketing, and quality management. We find the Kano model important because it bridges the gap between customer expectations and product innovation. It ensures that resources are invested in features that genuinely matter to customers while avoiding over-engineering. This model aligns perfectly with our commitment to delivering user-focused solutions, enabling us to strike the right balance between functionality and delight. By applying the Kano model, we can prioritize features for our product that address both functional needs and customer desires. For instance, when designing a new measuring caliper, we would ensure that the digital display meets performance needs, while the suction cup tip could serve as an excitement feature that enhances usability for measuring round objects. And a basic need would be having something that could actually be handled in human hands and isn't too big or too unwieldy. The Kano model excels at categorizing and prioritizing customer requirements, helping teams focus on impactful features. However, customer preference evolves over time, and what once an excitement need may become a basic need. Regular reassessment of customers' expectations is essential to ensure that the model remains effective. The minimum viable product concept focuses on creating a product with just enough features to satisfy early adopters and provide feedback for future development. The goal is to bring a functional product to market quickly, test its core value proposition, and refine it based on real world usage. MVPs are widely used in software development, startups, and product innovation, allowing companies to validate ideas without investing heavily in full scale production. We evaluate the MVP approach because it emphasizes speed, efficiency, and learning. Instead of spending months perfecting a product that might not resonate with customers, MVPs allow the team to gather user feedback early and pivot if necessary. This iterative process aligns with our belief in design customer-centric solution while minimizing the risk and waste and effort. In our project, developing an MVP would help us test concepts before committing to a full-scale production. For instance, a simplified prototype or measuring caliper with basic digital functionality could validate the core idea, and feedback from early users could guide further development to add features like suction cups or advanced display options. It could also tell us whether or not we need to go back on a couple of ideas like having an electrical component and maybe go for something more analog, just allowing for a shift in the product. The MVP's strength lies in its ability to gather customer feedback early, reducing the risk of costly mistakes. However, its limitations include potential misinterpretation of product value if the MVP lacks polish. Additionally, the feedback loop on sometimes lead to over-adjustment, requiring a careful balance between iteration and vision.
First, to start out with automation, I'm going to talk about robots and cobots, also known as industrial robots or collaborative robots. They are used in manufacturing and design to work alongside humans in safe environments and are equipped with many advanced sensors that help monitor and contribute to the manufacturing process and also contain safety features that facilitate safe collaboration with human workers. The non collaborative robots will usually work isolated from people and contribute to tasks that require large systems such as MIG welding, car chassis, or palletizing heavy boxes. Quality inspection is another useful utilization of these robots. Some examples in assembly are they can be used for part selection and orientation, dispensing of glue and adhesive, welding, application of paint, surface treatments, soldering, fastening of screws, bolts, and nuts, or finishing steps such as polishing. I find this topic interesting because it is highly likely that in the future, all factories will be 100% autonomous, requiring no human interaction. With these tasks, the automation increases efficiency substantially and reduces errors with their precision. The implementation of robots and cobots can be limited by the cost and effort it takes to train and maintain them. And currently, cobots also have limited task suitability and require more human help when unusual events occur. And next, I'm going to go into the Industrial Internet of Things, or IIoT, which is a collection of sensors, instruments, and autonomous devices that are connected through the internet and used specifically for manufacturing, which is unlike the regular Internet of Things, which it derives from. As of recently, AI is a big concept in connecting the robots for these systems of internet connections with the manufacturing. And it's really fascinating how the improvements that can be suggested by artificial intelligence could increase efficiency within manufacturing. These systems are able to gather data and carry out analyses to optimize production and therefore the efficiency and cost of it. They are also capable of understanding consumer demands to improve the design and manufacturing process. However, some limitations include, like previously mentioned with the cobots, the high cost of implementation, and in fact, it would be complex to integrate within certain uh, factory settings. Also of major concern are the security vulnerabilities because of the extensive sensitive data collection that could be cyber attacked, unlike typical systems of sensors and such within a factory. Lights out factories are another form of automation in industrial manufacturing in which these fully automated factories produce with all lights off, hence the name. Many are proven able to do so because of manufacturing operations management software, but because achieving full lights out factories is a difficult task, many factories have lights out manufacturing cells or light sparse factory floors in which only specific tasks that are easier to implement have lights off. Being able to run 24/7 allows for a big increase in these factories in terms of productivity. And with no need for human labor, there's a large cut in costs and the reduced risk of dangerous accidents occurring in the workplace. Beyond that, these factories include the same benefits I mentioned previously with automation and the robots and cobots. But also, as I brought up with light sparse factories, it can be very difficult to use this method with increasingly complex products. So the removal of humans in the process, unfortunately, also increases the chance that there are malfunctions that go undealt with and could compromise the safety of the whole system. I added this graph here that displays the increase in the topic of lights out factories over time, and it's interesting to observe here that as of recently, there's been a slight downward trend, likely due to how increasingly complicated it has been proven to implement the full light out factories. This is especially true with the increase in the complexity of products that are being manufactured today and the need of monitoring for the assembly of these products. And now I'm going to discuss retrofitting, which is the concept of adding new engineering features to older model machines or upgrading a machine instead of throwing these older generations out completely. It isn't as new of a concept to production, but it is really interesting as it is still increasing improvement to this day. The most important aspect of retrofitting is greening, and using this method is very energy efficient because older parts aren't being replaced but rather improved upon, which saves the cost of reimplementation. These new features that are added also allow for overall a better performance and more optimization in the manufacturing process. But however, retrofitting can't always be done due to potential compatibility issues between parts and machines, as well as space constraints they could have. It could be these additions don't achieve the same level of performance as a completely new machine as well, and installing these new parts and features also takes time and could significantly disrupt production.
Augmented reality is the use of overlaying digital information onto the real physical world, enabling enhanced interaction with real-world environments. In design and manufacturing, AR applications include prototyping visualization by designers to project 3D models onto physical surfaces, manufacturing guidance by providing workers with real-time instructions, maintenance and repairs by allowing technicians to overlay step-by-step repair instructions, and quality control by comparing products to digital models in real time. We like augmented reality because it bridges the gap between digital and physical worlds. Augmented reality enhances product design by enabling designers and clients to interact with digital prototypes in real-world environments. This leads to better ergonomic and aesthetic evaluation before production. They can integrate AR into assembly lines for real-time monitoring, improving efficiency, and reducing training time for workers. The big capabilities are its enhancement in precision for tasks through visual overlays, the improvement of worker training with interactive step-by-step guides, the reduction of prototyping and troubleshooting time, as well as the requirement of specialized hardware like augmented reality glasses or tablets. The integration with legacy systems can be challenging, and the limited field of view in some AR devices restricts usability. Extended reality encompasses augmented reality, virtual reality, and mixed reality. Extended reality creates immersive digital environments and combines real and virtual elements, offering broader applications than any of the three by themselves. Extended reality can be applied in manufacturing and design through product design, training simulations, collaboration, and process optimization. We find XR compelling because it enhances creativity and collaboration, making it possible to innovate faster. The immersive nature of XR enables thorough testing and evaluation of designs, ensuring they meet user needs before physical production begins. Using XR, we can test designs in virtual environments to assess functionality and user interaction without creating physical prototypes. In manufacturing, XR can optimize workflows by combining real-time data and virtual enhancements, such as visualizing how layout changes impact production. XR is capable of fully immersive environments to allow for detailed design testing. It facilitates global collaboration in shared virtual spaces. It simulates real-world conditions for worker training and product testing. However, it is limited by requirements of powerful hardware and software systems. Immersive environments can also cause some discomfort through VR motion sickness, and often this is a high cost of implementation. It limits accessibility for smaller organizations. Thank you for listening to our presentation.